calculators and topological orders. So today I would like to talk about this issue of it's possible to unify the topological invariants and all the dimensions and symmetry classes into a single form, and then write it into the so-called topological marker. Yeah, and also so this is very much related to what Kyle was talking about in the first talk, and also I will draw some connection with what the so-called quantum metric as the second talk by Thais. So the outline of my talk, as I have actually just mentioned, so I want to first unify all the topological invariants to give a grand unification of topological order, and then propose this so-called metric curvature correspondence, which part of the conclusions you have seen in Matthias' talk a little bit earlier. And then finally, I will introduce a universal topological marker. So the story goes like the following. Yeah, in the previous talks, you have so Kyle has mentioned some systems, some topological systems in 2 dimensions. But if you want to discuss all of them in a sort of unified manner, then unavoidably you have to go through this so-called symmetry classification. So it goes like this. So in general, all these topological materials, at least the low energy part of it, will be described by the Dirac Hamiltonian, where you have this D vector, which characterizes your momentum dependence of the Hamiltonian, and you have this Dirac matrices that satisfy the Clifford algebra. And then the material has a gap, and then you have this field valence band or quasi-Hall state, and you have this empty conduction bands or the quasi-particle bands, right? And all these materials have been classified according to the time reversal particle and chiral symmetries defined in these manners. And the result of this classification is this very famous table of the so-called periodic table of topological materials, where you have 10 symmetry classes according to whether it has or has not time reversal and particle Hall symmetry, and whether this time reversal and particle Hall they square to +1 or -1, and the product of these two is the so-called chiral symmetry here. And the interesting thing of this periodic table is that it repeats every 8 spatial dimensions. So you see that Z and Z2 and all that mean that their topological invariants are integer values or binary 1 and 0 or even numbers with 2Z. It's very nicely proposed by these pioneering works. Now, the question is, how do you exactly calculate these topological invariants, and what do they correspond to experimentally? For instance, if you just take the systems from 1D to 3D, the relevant systems to our everyday life, right? So then you look at this blue, there's actually a big zoo of topological invariants. So you look at this red, these are the 1D systems that are so calculated by the so-called Zach phase. And namely, it is the integration of this so-called Berry connection over the Brillouin zone. And it is shown to be related to the so-called charge polarization of the one-year states or some variations of it. And showing to this purple, you have this 1D Majorana number that gives you the Majorana edge modes that you can appear in this system, in this so-called 1D class D. And then showing in this orange, you calculate these classes by using the time reversal operators of the systems. And they are corresponding to the quantum spin Hall effects that Kyle was mentioning. And then coming to this blue, you have these Chern numbers that are related to the Hall conductance in the quantized in the quantum Hall effect, and also related to the so-called TKNN formula. And then you have a 3D winding number if you go to 3D systems. So in other words, there's a big zoo of them. Now, the simple question that we want to ask is whether it's possible to, is there some unified description of all these different kinds of topological invariants? Yeah. And it turns out that in this very nice review paper by Chu, Teo, and Schneider and Rio, that they say that there actually is some kind of unified description. Namely, if you, instead of looking at the Dirac Hamiltonian, you look at this so-called spectrally flattened Hamiltonian, where this the k dependence of the Hamiltonian is divided by its module, And therefore, the eigenstates, the eigenenergies of this spectrally flattened Hamiltonian is always +1 or -1. And then in this periodic table, if you look at these ones that are odd dimension and have chiral symmetries, then all of them can be calculated by the so-called winding number. Namely, you take this spectrally flattened Hamiltonian and you calculate its derivative, and to the d times, namely you calculate in all the spatial dimensions, take a trace and integrate it, it must be a quantized integer. Yeah? And coming to this this green, you go to the even dimension non-chiral symmetries, and you have this so-called Chern numbers that you also calculate from this spectrally flattened Hamiltonian in this particular way. Yeah. And then the rest of them are the so-called first and second descendants. That you also calculate these numbers, and then you just go to -1 to these powers. So that's why you got the Z2 invariant for these classes. Now, the question we want to ask is that we are still not very satisfied with two invariants. We want to unify them into one formula. So this comes to our introduction of our theory of this so-called wrapping number that we introduced. Or we also call it the degree of the map. It goes like this. So once again, you start from this Dirac Hamiltonian, and you define this unit vector in the spectrally flattened Hamiltonian, which I call n of k. I'm very short, so let me stand here. Then, so the degree of the map between the Brillouin zone torus and what we call the Dirac sphere, where this n of k forms, is taking this form. So you take every component of this n vector, combine it in this fully anti-symmetric wake, and then in between them you insert this derivative over each direction of a momentum. Then we claim that this is a universal topological invariant for any one of them on the periodic table. Now you can actually visualize this process. So it goes like this. So as an example, the simplest example in 2D is this so-called lattice model of a Chern insulator, where you have the d vectors are the Hamiltonians is expanded by the Pauli matrices, and these d vectors, they have some momentum dependence written as the following. Now you can plot this n vectors, which are this d vector is divided by its module, as a texture of unit vectors in two-dimensional space, because there are three component vectors in a two-dimensional Brillouin zone, so they look like this. So you can imagine a process. All these blue vectors are the n vectors, right? So you can imagine a process that you shrink the base point of all these blue vectors together to form together, then they're gonna all pointing kind of to the North Pole, as you can see from this figure, right? And obviously they are all unit vectors, so they will form a sphere. So this wrapping number is counting the number of times that the Brillouin zone torus, well, although here is a square, but you remember that it's periodic in both directions, so it's actually a torus. How this torus wraps around this sphere. As you can see, most of them are just pointing to a North Pole, right? So it means that your Brillouin zone does not even map around the sphere once. So the wrapping number is 0, or the degree of the map is 0. Whereas in this topologically non-trivial phase, so this parameter m is negative in the center, so you see that in the center you have this blue vector pointing downwards. So if you shrink all of the base point of all these vectors together, then there will be some of them pointing upwards and some of them pointing downwards. If you use this wrapping number to calculate it, then you're gonna see that the Brillouin zone wraps around this Dirac sphere once, yeah? So, and by the way, this quantity in differential geometry has a name. It's called the Kronecker index of a vector field, or also called the Brouwer index of a Brouwer degree of the map. So, okay, so why do we claim that this is really universal? Because you can prove that these, in this odd dimension with chiral symmetry, these winding numbers are exactly equal to our degree of the map. The reason is very simple, because these derivatives of this spectrally flattened Hamiltonian, if you take a trace of them, it's nothing but a trace of all the Pauli matrices all the Dirac matrices multiplied together, and plus the fact that Dirac matrices are anti-commute, so you naturally have this fully anti-symmetric tensor in front of it. And also you use the fact that the trace of all the Dirac matrices multiplied together is a constant. Then you get rid of it, then you just get the cyclic derivative that I showed you in the previous page. And in this even dimension and without chiral symmetry, the logic is also the same. You just have the trace of some of this derivative, but still trace of all the Dirac matrices multiplied together is the constant. And also, you know, Dirac matrices are anti-commute, so they naturally give you this tensor in the front. Okay, and then the first and second descendants, once again, are just -1 to the power of this. So with this, then we very nicely unify all the topological invariants on this periodic table into this degree of map. So the topological invariants are either the degree of a map or -1 to the degree of a map or 2 times degree of a map, depending on whether you are in this periodic table. Yeah. Now you say that, okay, so you got this, but so what? I mean, is there something interesting that can come out with this formula? Now this brings us to the issue of the quantum metric of the Dirac materials. So we found that, first of all, let me give you a brief introduction of quantum metric, although Matthias and also Thais have already mentioned this. But let me say it within the context of Dirac models. So if you have Dirac models and you focus on this n-particle field band state, either the valence band states or the quasi-Hall states, and remember they are fermions, so you need to make them fully anti-commute. Then you can construct a quantum metric from the overlap of these valence band states at momentum k and a slightly different momentum. Yeah, and because these valence band states, you can visualize it as a unit vector in the Hilbert space. So it's going to point at some directions in the Hilbert space. For instance, if you have 3-dimensional Hilbert space, then it points in some, it's a unit vector that points in some direction. Now, once you go to a slightly different momentum, then this unit vector is going to rotate to a different direction, right? And then you can imagine a process that you take a dot product of these 2 unit vectors. Now you know that the dot product of 2 unit vectors can only be less than 1. So if you write it as 1 minus some corrections, then you can prove easily that the leading order correction is quadratic in this small delta k you have moved, and the prefactor just gives you the so-called quantum metric. Yeah. And if you write it literally, it looks like this form. And from a very simple calculation, you can show that for Dirac models in any dimension and any symmetric class, this quantum metric takes this field by form that is that you use in general relativity, right? So this thing that the dot product that generates your quantum metric is called field by. So okay, now you have this. Then what is interesting is the following feature. Namely, if you go to our universal topological invariant, constructed from this cyclic derivative of these n vectors, now because it's fully anti-symmetric, so you can write it into this determinant form. Then it is very easy to prove that this integrand, which also plays a role of the Jacobian of the map from torus to this Dirac sphere that I show you, turns out that the square of this Jacobian is just the determinant times determinant, and multiplied together looks like this. And moreover, you know that this off-diagonal parts will vanish because the derivative of a unit vector is 0. So it turns out that it is becoming the determinant of this derivative of the field by form as well. So in other words, it means that the module of this universal topological invariant is equal to the square of the determinant of the quantum metric. Now this is very nice because it means that if you can manage to measure the quantum metric by some means, for instance, by this nonlinear quantum Hall effect stuff that Thais was talking about, then maybe you have a chance to measure the topological invariant in any dimension and any symmetry class. Yeah. So Right, so we call this the metric curvature correspondence, as been discovered in our previous work. Now, we also have some proposal to measure this. Instead of doing it in real space, which you need to integrate over the quantum metric or the quantum metric dipole and so on, is it possible to measure it directly in momentum space? Now, we think that this is entirely possible in a pump probe kind of experiment. Yeah. So the theory goes like the following: suppose you shine the gap materials with some pulsed shape of light that is polarized in some directions. Now, in the perturbation theory, you know that this pulse shape, because it's polarized in mu direction in real space, so in momentum space, it will correspond to derivative over momentum, right? Then the Fermi-Golden rule will tell you that the transition rate at a specific momentum as caused by this pulse is nothing but a Fourier transform of this pulse at this particular momentum that you're measuring, multiplied by this matrix element, which is derivative of the derivative of the field band and empty bands, which turns out to be also equal to the quantum metric. Yeah. So, so this means we have a kind of, we propose this quantum metric can be measured in some kind of loss fluence spectroscopy. Namely, you just give it some pulse and you measure how many electrons are pumped into the conduction band. And you divide this two, the coefficients will be exactly the quantum metric. Yeah? And this should be valid for in any dimension. So now, we think that this is fully possible for graphene, and actually this kind of experiment has kind of been done. They just didn't interpret it in this way. So let me go to this slide of, let's say, starting from the band structure of graphene solved by type binding model. So you know that, so now I want to discuss the possibility of measuring the quantum metric in graphene and to reveal the topological order of it. So suppose you have a time binding of graphene whose band structure looks like the following, right? And as you have seen in Matthias' talk, that the graphene contains these topological charges for each one of these Dirac points. Now you calculate these topological charges by taking a trajectory that circulates the Dirac point, and you calculate the so-called Berry connection along the azimuthal direction and integrate over this angle. Then you're gonna get a quantized integer. Now the point is that this is topological because it does not depend on how big is this ring, this circular trajectory, as long as it circles one of the Dirac nodes. Yeah. Okay. Then and the metric curvature correspondence in graphene looks like this. It turns out that this Berry connection is the square of it is directly given by this azimuthal quantum metric in the azimuthal direction. Yeah. And in experiments, they can shine. So the prediction is that experimentally, if you shine a pulse light and they measure it in terms of this like intensity of a light, they call it the fluence. If you shine graphene with the polarized light with a fluence 10 to the minus 4 millijoule per centimeter square, which is entirely doable experimentally, the prediction is that you can cause you can excite about 10% of the electrons from the conduction, from the valence to the conduction band. And you divide this two, you will get a quantum metric. And then this thing will be also equal to a topological charge. Yeah. And let me try to mention that this kind of experiments have actually already been done. This is the Gertz et al. Experiment that is done on graphene. So what they did is they shine a pulse light of graphene, and they see that this is before the pulse, this is during the pulse, and this is after the pulse. And here they are measuring a specific momentum here showing in the blue. And you see that during the pulse, some electrons are gone, right? Because they are excited to the conduction bands. So what we're saying is that if you can manage to quantify the loss of this and divide it by the intensity of this guy, then you should be able to measure the quantum metric and hence the topological charge. Yeah. But the message to experimentalists is that you need to use polarized light in order to fix your direction of the quantum metric. And also here I want to mention again, there are many other intriguing applications of quantum metrics, such as the one that is already given in the Matthias' talk. And let me just mention again, we predict that, or we verify that the opacity of a graphene is actually a topological charge. And as a result, when you see a graphene, single layer graphene, for instance, like this one, you can actually buy it commercially, graphene on PET or on glass-based film. The opacity, the fact that you are seeing 2.3% of the opacity against any color and any polarization of the light is because you are seeing the topological charge. And this also implies that the fine structure constant is topologically protected, and also all the 3D TI films of any thickness should have the same opacity. And what Matthias forgot to say, the most important thing of his talk is that he's graduating soon and he's looking for a postdoc position. So if you have any good opportunities, please let us know. Yeah. And then we also discovered that S-wave and D-wave superconductors, the quasi-host states of these S-wave and D-wave superconductors actually have quantum metric too. And for this, I refer to you to David Porter's poster on Thursday. Yeah. So what we are saying is very interesting. If you take this Bogoliubov coefficients that you learned in the textbook, and you plot it as a two-component vector field, this UK and VK. If you plot it as a two-component vector field in the d-dimensional Brillouin zone, then the quantum metric is nothing but the twisting of this quantum metric. You see that here, it twists a lot near the Fermi surface, right? So it turns out that this twisting is just the quantum metric. Well, for the D-wave superconductors, if you plot the normal state dispersion and the D-wave order parameter as a two-component vector field in a two-dimensional Brillouin zone, then you see naturally that there's a winding of these vector fields, as you can just see by your eyes. And this, we argue that is a topological charge, and it turns out that is also also related to the quantum metric in these D-wave superconductors. Yeah. So this means that you might be able to see this topological charge by some optical means. But this we are not quite sure yet. Yeah, okay. So finally, to the second part of my talk, I will try to rewrite this universal topological invariant into real space to a universal topological marker. So the procedure goes like the following. It's a little bit mathematical, but nevertheless, I will go through this quickly. So the claim is that this degree of the map, which takes this cyclic derivative of these n vectors, can also be written as the trace of this W matrix, which is the unused Dirac matrices in your Dirac Hamiltonian. You know, at a specific symmetry class, sometimes you use all the Dirac matrices, sometimes you don't use all of them, because sometimes you use some of them to interpret your symmetry operators. So if there's some unused one, you multiply all of them together, you call this W. Then in this spectrally flattened Hamiltonian, yeah, and you combine it in this, you multiply by d plus 1 times, and in between them, you insert this derivative over momentum. Yeah. So the claim is that the degree of a map is equivalently this one. And also I want to mention that this, this spectrally flattened Hamiltonian is equivalently the projectors to the conduction band minus the projector to the empty band. Because this is spectrally flattened, so the eigenvalues are either 1 or minus 1. So naturally, you are projecting to either the eigenstate in the positive eigenenergy or negative eigenenergy. So the proof is very simple, because in this form, if you just, once again, is actually the same proof. You take a trace of all the Dirac matrices multiplied together, then you get a constant. And plus, the Dirac matrix is an anti-commute, so you naturally will have this fully anti-symmetric Levi-Civita tensor in front of it. And moreover, the derivative of this spectrally flattened Hamiltonian is equivalently either derivative of this projector to the field band or projector to the anti-band. The reason is because these two combined together forms identity matrix because they are a complete set. Yeah, so this is true. So and then the reason that you wanted to write it into this particular form is because you can split them into this two arrays of projectors to the empty band and filled bands, and like P and Q, and alternating together, the first array. And second array is also P and Q alternating together, but you start with the P. Then the reason to write it into this is because when you make a product of them, you will always get the product that looks like the valence band product with derivative of the conduction band, or the conduction band productive with the derivative of the valence band. Now, this is very nice because then you can use this, this famous Chern-Marker paper formalism to say that this kind of derivatives is always equal to the wave function, the full wave function sandwiched by a position operator, and the wave function of the conduction band. Yeah, and together with this, together with the fact that you have a momentum integration in the front, so you're gonna get a lot of things that looks like momentum integration of your full valence band state. Then this is equivalently, if you want to translate it to the language of lattice model, this is nothing but a summation of all the positive eigenenergy states. Then you can define this big Q, which is the projectors to the positive lattice eigenstates. And likewise, this one, integration of all the valence band states and different momenta is equivalently the projectors to all the negative energy states in the lattice model. In this way, we have already written this wrapping number into entirely an object defined on the lattice Hamiltonian. Yeah? So this way, we introduce something what we call the topological operator. So it looks like this. First of all, you have a product of all the unused Dirac matrices. And second of all, you form two arrays of alternating projectors. The first one started with Q, the P, and so on, QP, and alternating, right? And the second one starts with P and Q and P and Q and so on. And in between of them, you sandwich by your position operator, depending on how many dimensions you have. And this formula is valid for any dimension. Yeah, if you have 5 dimensions, if you want to have fun with topological materials in 11 dimensions, then you sandwich 11 position operators in between. They all work. So the claim is that the diagonal elements of this operator will give you the local topological marker that should be quantized to integer. The off-diagonal elements of this turns out to be equal to the Fourier transform of this integrand of this universal topological invariant. Now, this thing is interesting because it should be able to detect the topological phase transition in any materials. The reason is because although the integral of this thing should be quantized topological invariant, right? But if you consider the Fourier transform of this, now this integrand itself should become more and more diverging if you're approaching a topological phase transition. Now, if you Fourier transform a diverging function, then you're gonna get an exponentially decayed function in real space. And because it becomes more and more diverging in momentum space, in real space it become more and more long range. Yeah? So this is what we propose to be a universal kind of correlation function for for any topological material. Yeah. So now in the last 5 minutes of the talk, let me just convince you that it works in all the models that you have in the market. So in every spatial dimension, you have 5 asymmetry classes that are topologically non-trivial. They are given by this Cartan group notation, group theory notation. For instance, coming to this class BDI. So here I'm plotting you a topological marker in 4 different parameters, where the red and green are the parameters that are in the topologically non-trivial phase. And as you can see, that they are quantized deep inside the bulk. And whereas the boundary, they have some anomaly. And this anomaly Kyle has mentioned previously in his talk. right? This turns out to be because of the way you assign the position operators. And by the way, we know how to fix it recently. We know how to assign a proper position operator to remove these anomalies at the boundary. Yeah, and whereas this blue and orange are in the topologically trivial phase, so you can see that deep inside the bulk they are all 0. However, if you look at the non-local marker, then the green and blue, green and what the color is this? Oh, red. The green and red, they are both in the non-trivial phase, but the green is closer to the topological phase transition. So it becomes more long range, as you can see. It will decay with a longer decay length, whereas the red is very, very, very narrow. And here as well, the blue and orange are both in the trivial phase, but the blue is closer to the phase transition. So you see that its decay length is longer. And you see that this feature is the same in all the symmetry classes. For instance, class D3, class D, and so on. Class D here is also constant here for the blue and green, but the green is more long range. Yeah, and blue and orange are both 0, but the blue is more long range here. And just to mention it, that this particular one is so-called the famous SSH model in class BDI. And this class D, what we are showing here is precisely the simulation for the Majorana chain. And by the way, the topological operator in 1D looks like this. You have only one position operator, so you just take PQXP and the second one PXQ. And then you put the whatever is the topological, whatever is the Dirac matrix that you did not use in front of it. And in 2D, it also works in the same way. So the topological operator in 2D looks like this. The churn marker turns out to be one special case of this more generalized formula where you don't have this W matrix because you have used all 3 Pauli matrices in your problem. And and here, what I'm showing you, the 5 symmetry classes, the first 2 are the churn insulator and the BHZ model that Kyle has already mentioned. And it also works for the 2D topological superconductors. These are the so-called chiral and helical P-wave superconductors. And here I also wanted to mention that experimentally, as I briefly mentioned to Gabriel, that we propose what is called the churn marker spectral function, or if you spatially average it, is the so-called churn number spectral function. Namely, the circular dichroism, the prediction is that the circular dichroism, as a function of frequency of these materials integrated over frequency, should be a quantized integer. For instance, if you are in a non-trivial phase, then this area here should be quantized. But if you're in a trivial phase, then you're gonna have some frequency that has a positive circular dichroism and negative circular dichroism, and they're gonna cancel each other out to give you a total churn number 0. Yeah, so in other words, this thing integrated over frequency should give you the churn number. And finally, coming to 3D, so once again, the feature is all the same, and the topological operator in 3D looks like this. You have 3 position operator X, Y, Z, so you need to alternate it 3 times. Yeah, so still it works. And in 3D here that we're using are the typical topological superconductors, namely this so-called B phase of helium-3, and class A2, right? Yeah, are these 3D topological insulators like bismuth selenide or bismuth telluride. Yeah, so as you can see, it still works. So, okay, here comes to the summary of my talk. First of all, I have presented a grand unification of topological invariant in terms of what we call the wrapping number. And secondly, I introduced this metric curvature correspondence, which indicates that it seems to be possible to measure all kinds of topological order in all kinds of materials if you can manage to measure the quantum metric. Yeah, and finally, I give you this universal topological marker, as I was showing you that they all show the same features in any dimension and symmetry class. And thank you very much. Yeah.
Thank you. Before the questions, I have an announcement. There is a car, a escort car, is parked outside. The plate is from Belo Horizonte. The lights are on. if it is someone from here. But if not, questions?
It's not my car.
So if I understood things correctly, your topological marker is the one that Kyle talked about, the one that has a certain sign in the bulk and a different sign at the edges. And he claimed that it was good for that reason that you said you can fix the problem. Can you explain how?
Okay, not just that. So first of all, what Kyle uses, if I understand correctly, is one kind of this topological marker. It's a 2D and is at one specific symmetry class. But what I'm showing you here is a formalism that applies to any dimension and any symmetry class. So potentially, what I mean to mention is that actually why you want to propose this topological marker, because you want to study what Kyle did, right? You want to study the disorder, you want to study amorphous materials, or you can study junctions, you can study grain boundaries, whatever. What I want to say is that this formalism make it all possible in any dimension and symmetry class, not just in 2D. Yeah.
So that solves the problem of the disordered system.
Yeah, so actually, yes. So we have recently started to study this. What happens if you put disorder? For instance, what happens if you put some disorder here? Then will this flat region still remain flat, and or is starting to kind of do something weird? And then, but you see, the interesting thing is because I have a marker that works for all the materials, right? Then you can study the disorder with all kinds of symmetries. Because, for instance, you can study, the issue is what happens if your disorder breaks the symmetry of your material? Does it matter, right? Or what if you have all kinds of long-range disorder and something like that? Yeah, so.
Yeah, so if you want to study disorders, you have to integrate that over the whole sample.
That's one issue. Or the second issue is you can study it locally. Or another issue, actually this is what we're studying right now, is whether the globally averaged marker remains unchanged in the presence of disorder. Yeah, so that would mean
a physical measurement, a response to a certain, I don't know, measurement that should be quantized.
Exactly.
Can be described even by the integral of this marker
yeah.
over the whole sample? Is that how it's done?
Well, this is the only one that we think of, this circular dichroism in 2D. Whereas in 1D and 3D, actually, I'm not sure if it's possible to measure it. Yeah.
Okay.
So this is very fascinating and also very confusing to me because of my lack of understanding. But you said that you can define the local or the parameter in some sort marker.
That's true.
So if you had actually the disorder, because I actually wanted to ask during Kai's talk, but I didn't get a chance. So can we locally define something like domains of two different topological orders separated by domain walls?
Of
and
course.
Then maybe a percolation problem? Is this even a meaningful physical picture?
Of course, yes. Like I say, the purpose of mapping it to real space is because you want to study all these kind of effects, right? And it's possible to do that, but we just haven't systematically done it because you have all kinds of symmetries there, and then you can break it the symmetry without breaking the symmetry. So it's how do you systematically study all the symmetry classes? That's an issue, right? Yeah.
What if you cannot write your Hamiltonian in this Dirac form?
That's a very good question. So this unification is possible only because I'm working within the framework of Dirac models, right? But if you want to go beyond it, for instance, in this Kent-Mealy model, you have spin-orbit coupling or something else that is other than the Dirac model. Then I'm not sure. Then I think you probably have to study case by case. Or maybe you have to construct a marker specifically for that system that goes beyond the Dirac model, which I'm not sure if it's possible in general.
A quick question first, and then maybe a second question that we can discuss in private.
Sure,
okay.
Sure.
First question is, of course, people have this mentality that topology is global property.
Yes.
But here you have a local marker.
Exactly.
Am I right to assume that that's because in this local marker, you encode the information of a global topology in this projection operator?
Yes, yeah, that's
Right.
right. But
These
the point is
projections
that
are
you have
global.
to combine them in the right way. To
Right.
get
Okay,
the-
I
get the
understand. Okay, that
image.
make perfect sense to me now.
Yeah.
A quick question that we don't have to finish, we can discuss in private,
Yeah.
is that if one were to aim for a universal marker for all this topology, what you do is very elegant and make a lot of sense. But isn't there a more pedestrian way of thinking about this is that since this is topology, it's all about singularity or non-analytic nature of the wave function in the Boolean zone, wouldn't that be automatically encoded in the branch point between the bands? I don't know whether you're familiar with the concept of branch point that Watercon talk
You mean
about.
the Green's function?
No. The band structure has a branch point. This is Watercon talk about this in the 60s. Those branch points basically mark how two bands meet in the gap. And those analytical structure, whatever non-analytical nature should be in the branch point, because all analytic function, we know the information are always in the branch point or the branch cut, right?
Okay.
So wouldn't that be another almost pedestrian way of getting the universal marker?
Actually, I'm not sure, but
I have
right.
a short
We should-
paper
we
on
should
that for
describe-
one
we should-
particular kind of topology, but I'm pretty confident that you can apply or generalize to all the possible topology.
But the question is, can you actually write it in real space? Is that
In real space, no. What you do
Yeah.
is that you focus on the branch point, which actually holds the magnetic monopole. And then you can see what's the charge of the monopole, right?
Yeah.
And then you can follow the phase transition. All these things can be done very trivially.
Okay.
But of course, this is not very elegant, just
I think
pedestrian.
I think you have to teach me about this.
All right, thank you.
Be nice. Yeah. Okay.
More
lunch?
questions?
No.
If not, let's thank the speaker again.
Okay. Thanks.